Hello everybody, Adam Lusek here, and today we're going to be talking about re-ranking in retrieval augmented generation or RAG pipelines. At a high level, re-ranking is the process of actually sorting the retrieved set of documents into a more relevant order, where the first set of documents are retrieved using our regular semantic similarity calculations and base embedding models, and then that retrieved set is then ordered by relevance or filtered in some way with an additional re-ranking setup. The reason this is useful is because in a RAG pipeline, the biggest thing that you actually want at the end of the day is truly relevant information being retrieved from your database to be passed as context to a language model to generate that contextual response. This is generally done quickly and efficiently using vector databases and base embedding models that can convert text into dense vector representations or numerical representations of the text that capture the semantics of that document. And while this approach is incredibly scalable and quick, the issue we start to see is that the top results from a base embedding model may not always be best aligned to the given query, which is where the process of re-ranking comes in, a second stage that reorders the initially retrieved set to better match the true information need. Generally, this is a little bit more of a processing intensive operation compared to our just regular vector calculations that we do in our first stage retrieval, which is why you want to do it on a subset that's already been retrieved. So that's what we're going to be going over today. A couple different approaches to actually re-ranking and how it plays into the two-stage retrieval augmented generation pipeline. We'll cover the cross-encoder architecture and the late interaction architecture, how it's different from just regular RAG, and how it plays a role into actually finding the most relevant content. Along the way, we'll be breaking down how the individual models or setups actually work, along with, at the end, a full demonstration of a two-stage retrieval and re-ranking RAG pipeline. But before we get into that, I want to come clean. Contrary to popular belief, I don't have a background in machine learning or computer science. Everything I know about artificial intelligence has been fully self-taught and self-practiced. And if I can learn these advanced topics on my own, I believe anyone can, especially if they have the right tools. Which is why I'm excited to let everyone know about the partner of today's video. Brilliant! Brilliant helps you get smarter or refine your skills every single day with an expansive library of thousands of interactive lessons covering things like math, science, programming, data analysis, and even artificial intelligence. What I like about Brilliant is that they've spent years designing an app to be effective for actual learning. Each lesson and course is filled with practical, hands-on problem solving that lets you actually get down and play with the concepts, which is exactly what I encourage as well. And just in line with how I like to educate, Brilliant approaches problems from first principles, helping you build the understanding from the ground up. You can turn curiosity into comprehension, with courses designed to build real skills and develop your intuition. It's especially exciting to see that they now have plenty of courses related to cutting-edge topics like artificial intelligence that allow you to not only just understand and learn what the different underlying neural systems actually do, but build timeless problem-solving skills while you're at it. You can become a better thinker and problem solver with every lesson, whether you're learning to translate your ideas into code, build formulas, design electrical circuits, or run simulations with data. To try everything Brilliant has to offer for free for a full 30 days, visit brilliant.org/AdamLusek or scan the QR code on screen. Or you can click on the link in the description. You'll also get 20% off an annual premium subscription. So before we go into how each individual re-ranking model works, it's best to have a quick revisit as to how the initial stage of RAG actually operates. The first stage relies on the aptly named embedding model to convert or encode some form of unstructured content, generally text, into dense vector representations, or essentially just numbers. And these numbers are meant to and learned through the machine learning process to capture the semantics or meaning of the content that's being encoded. And so being able to capture the meaning of a word into a list of numbers allows you to do all sorts of mathematical operations then to that idea. The most common and popular of which is, of course, semantic similarity, which is comparing directly to encoded pieces of content. And this is, at a high level, the backbone of how semantic-based retrieval or semantic similarity-based retrieval works in a retrieval-augmented generation system. Now, I'm not going to go too much into the specifics of exactly how this works and how this encoding works. I implore you to check out some of my other resources, which I'll have linked in the description below, that go over this in a much more detailed manner, as we'll just be focusing on re-ranking. So usually the way that the first set of ranked documents, which are generally ranked by their cosine similarity or semantic similarity, is retrieved is through using a bi-encoder architecture. If you've set up a vector database or some sort of retrieval system before, you're likely familiar with actually how this works, but you might not know it exactly by the name bi-encoder. It's essentially just this first stage of retrieval, where we take a base embedding model and independently encode all of the documents into the numerical vectors or embeddings that capture their meanings. These pre-computed embeddings are usually then stored in the vector database. And then what happens is at runtime, a query is sent through the same encoding model to be converted into an embedding, and then that embedding is compared against the already computed set of document embeddings. Most often, this is using something like cosine similarity, which is essentially going to measure the distance between the two embeddings in the vector space. This is very similar as finding the distance between 2 points on a Cartesian plane. But the bi and bi-encoder mostly represents how we use two encoding models to do this calculation. One for the documents and then one for the query. Usually these are the same weighted model, so you're going to be using the same embedding model for both embedding your documents and then converting your query to do the searches. As I mentioned, this is the regular form that most vector databases take for just simple retrieval and embedding into the databases. So you've probably interacted with something like this, although you might not have seen it at a more technical level. In the context of ranking, this is of course the first step of the RAG pipeline as mentioned, where we can retrieve the initial set, but it does do some sort of ranking as well, usually from the similarity score between the retrieved documents and the embedded query, with the more relevant documents being ordered at the top and then going down in a descending order. So let's take a quick look at this initial ranking and retrieval in action. We're going to be using All-Mini-LM L6v2, a very popular embedding model that is able to take in some form of document or text and convert it into the 384-dimensional dense vectors. So after loading the model using the sentence transformers package, we can define the query and our candidate documents for retrieval. Our query is going to be who is the best technical AI YouTuber, and then the three potential documents that we would want to retrieve, or at least calculate the similarity for, are the dogwood is the state flower of North Carolina, Adam Lusek makes videos about artificial intelligence, and the Canada goose has a lifespan of 10 to 24 years. We can then encode our query and see what one of those dense vector representations looks like. And after running it through the model, we'll see the first 10 dimensions, or essentially the first 10 items in the list of 384 that this has been encoded to, look a little bit like this. And of course, these numbers are meant to and are learned through the model to capture some of the semantics and representations and ideas about the actual content that we're putting through it. So you can think of this as one of the first encoding steps in the bi-encoding process. The second then is of course to encode our documents. So we can run our documents through that and then compute this similarity. So by comparing our query vector to our document embeddings, we can get the cosine similarity between them. And from the output here, we can see that the more similar, which the higher number in this case is going to be more similar, output is the second sentence to our query. So it's saying that Adam Lusek makes videos about artificial intelligence is most similar to who is the best technical AI YouTuber. Now, I wouldn't disagree with that myself, but we can see that this gives us then an initial ranking. And this ranking is usually what's used to do the initial retrieval in the first stage of a RAG setup. Of course, this retrieval is done a lot more efficiently and quickly with all sorts of specific vector database architecture setups, but you get the idea. The higher similar documents are going to be ranked higher and thus what are retrieved as our initial set. So then our goal is to take that initial set and then do one more additional filtering and ranking process, which is where the literal re-ranking models then come in. The first of which being the cross-encoder, which the cross-encoder essentially is extending what the base embedding model does. In our prior setup, the embedding model is going to take in just a document independently or just a query independently and then create the output representation, but a cross-encoder is going to use the same embedding model but take in both the query and the document at the same time. It's able to do this because we've taken the base embedding model and trained it now as a classifier. So in taking in the two sequences, the query and the potential document, what we're going to do is output now instead a classification score or a predicted relevancy score. And training embedding models to become classifiers isn't anything out of the ordinary. It's actually a very popular thing to do because you can rely on the already pre-trained understanding of semantics and language that are done through the base embedding model, and then use that and apply one more additional layer onto the underlying architecture, where as all of that information is processed and through, we can output some form of classification or prediction. So we don't have to train an entire model to both understand language and how things interact together, as well as do the classification. You can just tack on a little bit of an additional step onto the already existing network. And the benefit of doing this is we can rely on how the actual transformers and attention mechanisms within a base embedding model operate to do direct granular comparisons of the tokens within both the query and the document. So similar to how the actual initial embedding and encoding works, where each of the tokens of the input sequence are going to attend to each other and create the final representation and vector, we're essentially going to use that now to compare the tokens of the query and the document together. And based on the understanding and additional classification training of the model, we can then output whether or not that query is relevant and to what degree to the document, essentially figuring out if pieces within the document answer the question of the query. In the end, taking advantage of this cross-encoding architecture allows for richer fine-grained interactions between the query and document and can yield a higher accuracy and more nuanced understanding and matching than our pre-computed embedding comparisons with biencoders. But as mentioned, processing both the query and every single document together in one forward pass of the model comes at a computational cost, as everything must be processed again and again, which is slower than our first stage similarity search, which we went over in the bioencoder architecture. This is why re-ranking is often applied as a second step in the retrieval process after a smaller candidate set has actually been retrieved from our initial bioencoder model. So let's check this out. We'll be using one of the similarly popular cross-encoding models, the MS Marco Mini LML6 v2. It is essentially the same kind of sentence transformer built that we used for the bioencoder, but this time it was trained on a passage ranking dataset. Very similarly to before, we'll be loading the cross-encoder model from Hugging Face, and then what we're going to do is define our query and documents. This time we're going to have what are the health benefits of meditation, and then I have 10 just random looking passages here about meditation. Some of them are more specific to the health benefits, others are similar yet not necessarily talking about health benefits, like this line here. Then what we can do is rank the query against the documents and see what the scores that we get out are. And we can see that on the left here we have our relevancy score, which was output by the cross-encoder, and it has ranked our documents. So we can see right at the top that research suggests meditation may lower the risk of heart disease by reducing inflammation and improving heart rate variability is at the top. You would expect this to be at the top because we are asking about the health benefits of meditation. And then down here closer to the bottom is that aforementioned line, something like the city of Kyoto is famous for its Zen temples where meditation has been practiced for centuries, which doesn't mention anything about the health benefits of meditation. It just talks about meditation. The interesting thing here is that naive retrieval might focus a little bit more on things like keywords. So it may surface a document like this last line here and say that it is similar to our query, but our cross-encoder has directly identified that of this retrieved set, it's not actually relevant to answer the question. Hence, you can see some of the benefits now of using a re-ranking setup to better filter your retrieved results that may be similar, yet not relevant to your actual query. And with that, we've covered the first popular approach to re-ranking, using a cross-encoder model as a second stage. Now on to our second form of the video, the late interaction model. Late interaction is a technique that was introduced with the release of Colbert, efficient and effective passage search via contextualized late interaction over BERT, and takes inspiration from both the bi-encoder and cross-encoder setup. Essentially, how late interaction works is we're going to take our query and document and break them down into their individual tokens. Each one of these individual tokens is going to be ran through a base embedding model and encoded into their vector representation. So in the end, for both our query and all of our documents, we'll be storing each individual token's encoding rather than the sequence's aggregated or pooled encoding. Then what'll happen is each individual query embedding is going to be compared to each individual document token level embedding. So we'll get a similarity score for each token level embedding to each token level embedding across the query and the document. This will create a token level similarity score matrix where we can see how relevant each token is to each other token is across the query and the document. Then for each token level embedding, the maximum similarity score from all of the comparisons here are kept. And then all of these maximum similarity scores are going to be aggregated together, either summed or averaged, and that computes our final relevancy score. So to repeat that real quick, each token of the query is going to be compared to each token of the document using some sort of similarity calculation, and then for each token, the maximum similarity score that is achieved is going to be kept. And then all of those maximum similarity scores are summed or averaged together to create our final score. And you can start to see how this is similar to both the cross-encoder and the bi-encoder, as we're not running all of this through a specific model. Rather, we're doing a little mix of pre-computed embeddings and comparison. This process can be thought of intuitively as similar to what's going on in the cross-encoder, as essentially we're trying to figure out what parts of the query are most relevant to what parts of the document. Except in something like this, we're going to be directly comparing the computed embeddings rather than using a classification-based model. Almost a little bit of a cross-encoder approach with a bi-encoder style. For the more mathematically minded among us, you can think of this as given a query queue with the tokens Q1 through Qm, and a candidate document D with the tokens D1 through Dn. We're first going to encode each token into a vector Q, which is going to be equal to the representation of Q1 through Qm through the embedding model, and similarly for D, so D1 through Dn through the embedding model. Then for each query token Q, we are going to calculate a similarity score that is going to keep just the max of the cosine similarity between each individual token level embedding Q and D. And then the final document relevance score S is going to be the aggregated sum or mean of these maximum similarity scores. The official research just does the sum, if you're interested in knowing that. So with the theory of late interaction down, let's actually load up the Colbert model and implement late interaction ourselves. Since Colbert uses kind of their own official repo, which you can check out here to do a lot of these late interaction setups, we're going to just use transformers and torch directly to simulate it and show in this demonstration process. The first step of this is of course going to be loading the tokenizer and the model from Hugging Face, which we will do there, and then define our query and documents once more, which are going to be the exact same from our prior setup. So let's load that through. And here's where things start to diverge a little bit. What we need to do is define two quick helper functions, one for getting the token level embeddings, and then one for computing the score. Our getTokensEmbeddings function is going to compute the token level embeddings through the model, take in the text, first run it through the tokenizer, and then split these into our individual tokens. Then those tokens are going to be sent through the Colbert model to create the representation for each, and doing a little bit of cleanup along the way. So you can see that implemented here in our function that takes in the text, tokenizer, and model, defines the inputs to the model, which is going to just run our text through the tokenizer, get the outputs from the model, which are going to be our representations, clean up a little bit of the actual individual tokens. There are some classifier separator tokens that may be in the output, and return back our final response, which is going to be just the token level embeddings. And then our second helper function here, the Colbert score function, is going to take in the query embeddings and document embeddings and run these similarity calculations, keep just the max, and then sum them. So after defining that, what we can do is actually rank the documents. So we'll get the query embeddings, the document embeddings, and then run through and score them and rank them by that score. So running that through, we can see on the left here, similar to what we had with our cross encoder, our relevancy scores, and then the individual specific documents. And so it's good to see that some of the similar documents that are more specific to actual health benefits are going to be at the top. And then similarly, the ones that are less so, but similar to meditation, but less so about its health benefits, are going to be ranked lower at the bottom. Now you might be wondering if there's two options to choose from, late interaction versus using a cross encoder model, why would you use one or the other? Well, the first obvious thing there is that you can rely on just using one model and doing these specific late interaction setups and not have to implement a second model into your pipeline. But also from the research, they found that this approach provides very comparable performance to existing cross encoders and other re-ranking methods, but was quicker and required a lot less computation. So with that, we now have two specific re-ranking approaches, late interaction and cross encoder models. So let's actually put these to the test and put together a two-stage RAG pipeline and see if our performance improves. For our example data, we'll be using the book The Adventures of Sherlock Holmes because it is public domain to use. You can grab it on Project Gutenberg, and they even have a very nice and easy to download plain text version. For my preprocessing, I'll just chunk this into first sentences and then combine these sentences into chunks of roughly 400 tokens. So let's run that through, and of the entire Adventures of Sherlock Holmes, we get about 380 chunks that look a little bit like this. So now with our data processed and chunked, we now need to embed that into a vector database. And I'll be using ChromaDB as it's super easy to set up and use for examples. And ChromaDB by default relies on the aforementioned All-Mini LML6 v2 base embedding model that we highlighted earlier for embedding documents and then also embedding queries at runtime. So we'll just create a client, create a new collection to store all of our chunks in named Sherlock Holmes, and then add all of our chunks in with a specific ID going from 0 to 380. So this is going to just take each individual chunk, run it through our embedding model to create into the vectors, and then those vectors are going to be stored along with the respective chunk in our database, ready for retrieval. So now we need to create our retrieval and re-ranking functions. Our first stage retrieval is just going to be a simple function that handles getting the semantically similar documents using Chroma's package. So we'll load our collection and we'll get our results by passing in our query and a number of results to the database, which in our case is just going to default to 25. And then we'll store all of those results along with their distance scores that have been calculated through the semantic similarity calculations into a nice list of dictionaries. This initial retrieve document setup, I'm not doing any sort of ranking yet by the actual distances, but this will give us our initial candidate set to be re-ranked. If you set up very simple RAG setups, you probably are thinking that the number of documents retrieved being 25 is quite a lot, and depends, of course, on your use case. as most people rely on somewhere around 5 documents to be retrieved and shown to an LLM. But in our case, we're retrieving all of these so that we can do that second stage filtering. So we need a good candidate set, and we want to retrieve likely more than not so that we can try and get the most relevant passages, which might not be picked up right at the top using our first stage retrieval. So now with our retrieval function set up, we need our first re-ranking function, which is going to be our cross-encoder re-ranking, which is going to do exactly the same thing that we did in our example before, grabbing all of the documents, predicting the score through our cross-encoder, and then sorting them in descending order by what was most relevant. And similarly, we are going to package up our example for late interaction nicely into our get token embeddings and Colbert score, which we're defining once more down here, along with our final function, re-rank with late interaction, which will get our query embeddings, and then for each document, get the token level embeddings for the document, and then compute the scores, and of course, sort the results by their scores. So now with all of our functions nicely defined, what we can do is just show quickly how they work. So our stage 1 retrieval with the query, show me moments where Holmes or Watson reflect on friendship, we can see if we retrieve 50, that it was pretty quick, and we have our semantic search only document set here. So this one is not ranked yet by how similar they are, but we see that we have some results. Then of course we can pass this set through our series of re-rankers. So we can do one with our cross-encoder here, and we'll see that what we get back is now our ranked score of each of these individual chunks, but now from the specific cross-encoder. And very similarly, we can now pass it through our late interaction model as well to do a different form of re-ranking. And so we see that there's some slight differences between the ranking between the cross-encoder and the late interaction model, but who are we really to say whether or not these are the most relevant? Let's actually slap a language model on top of these for the full RAG pipeline. Now putting it all together for having our query come in as an input, a set of documents being retrieved, then those retrieved documents being sorted by relevancy, and then the most relevant being passed to a language model to provide a generated answer, we are going to define this RAG response function here, where essentially we're taking in our query, the type of ranking, and the number of documents that we want to provide to the language model as context. So after just instantiating our OpenAI client, we do the first stage of our RAG retrieval, retrieving 50 candidate documents based on our query using just the by encoder semantic search setup. Then, depending on what kind of ranking we set, either we're going to do no ranking and sort those by the semantic similarity from the by encoder, or we'll pass all of these through the cross encoder or the late interaction architecture that we have. For demonstration's sake, I'll also print out a little bit of what chunks were actually provided as those top 5, k equals 5, from the different ranking steps. And we combine all of those documents together and pass them through a super simple prompt. You are a Sherlock Holmes expert. Use only the following passages from the stories to answer the question. Then we pass in the context as well as the user query and some instructions that if you cannot find an answer in the passage, reply the answer is not shown in the provided context. Otherwise, answer as specifically as possible using the text above. And then we send this prompt, which now has the loaded and ranked context and the question to GPT 4.1 to get our response back. So let's see how each one of these do. First, we're going to do no re-ranking. So essentially just relying on the most similar retrieved chunks from our by encoder setup through ChromaDB. We see our provided chunks, and then what we get back here is a response from the language model where it points out that Watson visits Holmes after Christmas and they had called each other a friend. And then in the same passage, they talk about the pleasure of each other's company. So there is a little bit that's actually been discovered here from the initial just individual part, but let's see if we can get this to be a little bit more accurate with our cross-encoder late interaction setups. Running through the cross-encoder, we shall see the top 5 chunks, which are a little bit different now from what we saw here in the top, and we get our response back. So they actually surfaced a passage where Holmes talks about his intimate friend and associate, Dr. Watson here, and then also how Watson reflects on his pleasure in accompanying Holmes, and all sorts of other things here where Holmes states that Watson is his only friend. So already we can see that re-ranking with a cross-encoder has surfaced the 5 most relevant chunks from those, and we get some much more clear examples that actually better reflect the query from what we had with just our naive individual setup. And so the hypothesis, of course, is that we will get something similar when using late interaction. So let's go ahead and send this through, and we'll see now that our 5 chunks have been retrieved, and we also get 3 specific examples where Holmes refers to Watson as his friend and partner. Watson reflects on his relationship with Holmes, mentioning their intimacy and role, so similar to what we had beforehand. And then the third one here is the continued visits to Holmes after marriage. So maybe a little bit different, but still, as you can see, much more relevant than just relying on our first stage semantic similarity-based retrieval. So we've been able to implement and prove that re-ranking does actually improve the performance of our hypothetical 2-stage RAG pipeline here, yet still nonetheless is effective. So to provide some summarization of what we've gone over today, I've put together a comparison table of regular retrieval and then our 2 re-ranking methods, late interaction and cross-encoding, here for your reference. But in essence, I would say that the bi-encoder is a recall-oriented coarse retrieval tool, while the cross-encoder and late interaction re-ranker is a precision-oriented fine re-ranking step. By relying on the traditional bi-encoder to quickly create a subset that can then be refined by a more compute-intensive re-ranking model, we can improve our retrieval results and downstream language model-generated contextual responses. So with that, hope you learned something interesting and are excited about implementing re-ranking into your RAG pipeline. If you liked the video, like the video. If you want to see more like this, consider subscribing. And if you really want to support the channel, consider dropping a super thanks or joining a channel membership. Thank you and have a great day.